Hello everyone, welcome to Electromagnetic Spectrum Lab channel. It is the second video of Quantum Optics playlist, especially in quantum well topic. In this video I want to explain how we can calculate electron wave function and eigenenergies of infinite and finite quantum well by using theoretical modeling. To get primary information about quantum well structures, I suggest to watch the first video of this playlist. The time-independent Schrödinger equation states that the kinetic and potential energy components sum to the total energy. In wave mechanics, these quantities are the eigenvalues of linear operator. It means this equation, where the eigenfunction psi describes the state of the system. Again, in analogy with classical mechanics, the kinetic energy operator for a particle of constant mass is given by this expression, where P is the usual quantum mechanical linear momentum operator. By using this form for the kinetic energy operator T, the Schrödinger equation then becomes as this equation, where the function V represents the potential energy of the system as a function of the spatial coordinates. Restricting this to the one-dimensional potential of interest here means quantum well. The Schrödinger equation for a particle in a potential well would be as this expression. For infinite quantum well, it is considered outside the well, the potential energy is equal to infinite, and hence the only possible solution is zero value of function psi, which in turn implies that all values of energies are allowed. Within the potential well, the Schrödinger equation simplifies to this relation. Hence the solution of psi can be obtained in form of this equation, which K, A, and B are the unknown parameters that are obtained by applying boundary condition and normalization condition. Consideration of the boundary conditions will yield the K and B constants. The only remaining unknown is the constant factor A, which is deduced by considering the normalization of the wave function. As psi star dot psi represents the probability of finding the particle at the point Z, then as the particle must exist somewhere, so this integral equals to 1, which gives a parameter. Now the final form of wave function psi for an infinite quantum well is obtained. By returning to the Schrödinger equation, we can obtain the energies of confined states as this equation. Now I want to talk about a quantum well with sandwich between two layers that are different from well material layer. Therefore, it creates a quantum well with finite barrier potential energy V0, representing the discontinuity in the conduction band edge between materials. For states confined to the well, the energy E must be less than the barrier height V. Therefore, rearranging the Schrödinger equation, it gives this shown equation. So a function is sought which when differentiated twice gives no change in sign of value. The exponential function fits this description. Therefore, we consider a sum of growing and decaying exponentials as psi function solution. In the left-hand barrier, z is negative, and hence as z decreases, the decaying exponential will increase to and without limit. Therefore, A2 coefficient must be 0. As the potential is symmetric, the eigenstates will also have a definite symmetry. It means they will be either symmetric or antisymmetric. With the region placed at the center of the well, the symmetric eigenstates will be in cosine terms, while the antisymmetric states will be as sine waves. So we can write psi function for well region as this relation. For right-hand barrier region, same as previous reasoning, the wave function is sum of growing and decaying exponential functions, which the growing exponential component must be rejected. By substituting the wave function in the corresponding Schrödinger equation, we can obtain the K1 and K2 expressions. To compute the unknown parameters, we should apply boundary conditions which are included the continuity of psi and first derivative of psi at quantum well interface points. By equating psi in the well and barrier, 4 equations have been resulted to determine the unknown parameters. Now by dividing 1 star and 2 star equations and also dividing 3 star and 4 star equations, the expressions of 1 and 2 are given. In the following we conclude b1.b2 is equal to 0, which states we have the solutions of psi for one of two parities, even parity states and odd parity states, because b1 and b2 cannot be 0 simultaneously. For even parity states, we have 0 value of b2 and psi is in cosine form, and in odd parity states, b1 equals 0 and psi is as a sine wave in the well region. In next step, according to the explanation and equation 1 or 2, for even parity states, we obtain a characteristic equation as equation 3. In the same way, for odd parity, the second characteristic equation is given. In both equations 3 and 4, we define M as the ratio of effective mass of barrier and well layers. Also, U, V, and U0 are defined as these relations. The total number of bound states may be found by dividing the maximum possible normalized wave vector, means U0, by the width of a branch and rounding this up to the nearest integer. There are many ways to solve the characteristic equation 3 and 4, but one common way is graphical method. By using this method, we can find intersect point of 2 plots as the solution. The first plot is equation 1, which is a circle equation, and second plot is a tangent or cotangent based equation. The black intersect point of 2 plots are the solutions of U and V. By resulting the considered U and V, K1 and K2 parameters can be obtained. For even parity states, according to the equations 1 star and 3 star, A1 and C2 coefficients are computed based on B1, K1, and K2 parameters. Finally, the complete form of wave function psi for even parity bound states is given. The remaining unknown parameter B1 can be computed using normalization condition. Similar to even parity states, for odd parity bound states, the unknown coefficients and as a result the complete form of wave function psi are obtained as what are shown in the slide. As an example, I calculated the energy levels and wave functions of two quantum wells with infinite and finite potentials. As you see, for finite quantum well, we have one bounded state with odd and two states with even parity. I hope you enjoy from watching this video. I try to cover most important information in this topic, and in future videos I will investigate more phenomena and details about quantum well structures. Thank you for watching and have a good time.